Thanks everybody for joining us today. I'm Mykyta. I work at WeFX, and I came to Canada like 4 years ago, and 3 of those years I'm working at WeFX, and it's been amazing. We worked on crazy projects, and I'm really excited to talk about one today. Yeah, so this is me, yeah, I'm from Ukraine actually, and I worked as a 3D modeler before, and then I just switched to FX because Houdini is much more fun than modeling, sorry. Yeah, before I jump into our presentation, I would like to introduce WeFX, where we specialize in creating visual effects for movies and television. Founded in 2020, in the beginning of pandemic, we quickly grew to a team of 130 artists, and our main focus is on creating hero characters and digidouble work, and along with environments and effects. We're also really proud to be contributing to the projects like John Wick 4, What We Do in the Shadows, Reacher, and and also Halo Season 2, which we'll be talking about today. Please let us show you the work that we do in WeFX. Thank you so much for your attention. So, as you probably already guessed, our pipeline relies heavily on using Houdini across asset effects and lighting. In VFX, we achieve great flexibility by implementing Houdini seamlessly across almost all of our departments. And this allows artists to work to iterate between the departments in a very flexible and fast manner, allowing very fast, desirable results. Finally, let's dive into what we did for Halo Season 2. And I want to present the sequence reel and the work that we did. Thanks so much. Yeah, so for this sequence, our main task was to visually illustrate the progressive awakening or activation of dormant or inactive alien virus. And we started from the microscopic view of the spores growing out, and then we transitioned to the widespread of infection within the human cells and human tissues. We received the storyboards, and we got it to have the initial idea of what needs to be done, and also start working on our effects setups and creating the assets. Basically, we took the essence of storyboards, and we worked closely with the clients by providing them with lots of iterations. And that's how we worked together to achieve the look that everybody was happy with. Here we can see some storyboards from around like 3 to 4 shots from this sequence, and then the storyboards for the rest of the shots. One of the main assets that we needed to create for this sequence was the asset of the spore. This asset contained around 3 million points, which was quite heavy. We initially thought of creating UVs and relying on texture painting and baking methods for texturing the spore, but we quickly abandoned this idea due to how volatile the resulting spore growth mesh was, because the point numbers were changing each frame and UVs were not stable at all, and we decided to go with procedural shading method. And we used surface curvature to drive the scale of subsurface scattering and also color and radius. And that's how we decided to go forward. In the beginning of the first shot, we had to develop the cell structures, and this is one of the earliest tests. We developed it in Maya and ZBrush, and then we transferred it to Houdini for further addition of procedural details. And also, here is the alien, the variant of the spore, which had the hooks growing out of it. And we used this for later shots when this spore needs to attack the human cell, infect it, and transform it to another alien spore. So we just modeled the hooks, and because we had the procedural shader already on the spore, we didn't need to do any additional look development, any additional look development work to be happy with the look. And also, this is the human cell that we did, and we developed it in Maya and then enhanced it in Houdini, like almost all of our assets. And the next big challenge that we faced with was creating a spore growth setup. Please check out how it looked again. Sorry. So as a first step for our spore growth setup, we needed to create a bunch of points so we can place the spore using copy to points onto. And we did that by scattering a little bit of points on the first sphere, assigning velocity attributes to those points. And using the custom solver to drive the positions of these points, we propelled the points outwards, and they took their positions. And then after that, we introduced more attributes to control the scale of the spores, the speed of them, and also how far they go. And everything worked together as a one set of nodes. And then by using attribute flow, we copied each set of nodes on top of another one, and by basically creating a spore level. And this logic allowed us to copy-paste each set of nodes to achieve more spore levels. Basically, spore level defines the new spores that come out of the previous ones. And here we can see that each each node box, a color of each node box corresponds to the color of the spores in the video. And here we just have 4 different levels, but we can theoretically copy it as many times as we want and to have infinite spore growth. And this allows the control of each spore level independently, but also all the other levels that come after that will take into account the changes that we made in the previous levels. So it works recursively. And this is one of the earliest tests that we did to showcase the possibilities of using our spore growth setup. Another challenge that we faced with is to have some interactions between spores when they come out of the other spores. So here we see on the left screenshot that when the spore comes out of its parent spore, it doesn't have anything they interact with. The intersection is very visible and it doesn't look that good. And we needed to come up with a quick way to resolve it and make some interaction. So by using the setup that we created, first we created an intersection attribute, basically to act as a mask and to see where the intersection is happening. And then we were using attribute blur to blur the normals between the points. And we used attribute blur by proximity, so it took into account all the points within certain radius, and it doesn't take into account the connectedness of the mesh. And then we added the resulting blended normal vectors to the point positions, and also masking by the intersection attribute that we created before. Yeah, and then like after we can see in the top right screenshot, we see the result of it by adding the positions to the normal of the, like we added normal vectors to the positions, and this is the result. And then because we used the procedural method, we had a lot of different artifacts and point jitter because of it. So we decided to use chop network in Houdini to filter all the point positions, basically, which produced pretty nice and organic results. And after using chops, we also decided to add some wobbliness to the spores by adding spring chop. Yeah, here we can see in the test scene that we created how it all was working, how the spores were interacting between each other. And the main point here is there is no solver, no vellum was used here. It's all procedural with some chop network magic. And the last but not least challenge that I'm going to be talking about today is the shot where we can see lots of alien cells moving towards the human cells and wrapping its tendrils around it and infecting it and eventually transforming the healthy human cells to the alien spores. In the beginning, we just received 5 different animations from our animation department, and each with different timing and attack animation to have lots of variations. Then we cached out each of the animation to the ASSS file, and then we placed it on the point position. Basically, we instanced this animation on each of the points. And to control the frame range of the animation, the frame number of each animation, we also used attribute, which is called frame number attribute. We basically had an integer value on each of the points that was driving each of the animation on each of the point per point. And because we had different variations on the animation, also we had a variation on top of the frame number attribute. Everything looked very natural and organic, and we were happy with the result of the variations. And that's it. Thank you so much for your attention. I'm going to be passing to my friend and colleague, Rafael, who's going to be talking about environment and in depth on how alien spore attacked a human cell. Thank you so much.
All right, hi everyone. My name is Rafael. I'm a senior artist at WeFX, and I'm also a Houdini teacher at Seneca, and I'm from Brazil. I'm a design by passion and FX artist by choice, and I joined WeFX back in 2022. So the next thing we're actually gonna take a look is how we built some of the environments for that sequence. So I'm just gonna play it one more time. Is it playing? And that's the topic of our next point, how we actually build that network, right? So how did we start? So we got some really interesting storyboards from the client. We had some discussions about how we could create that visually. So the designer in me kicks in. So I look for features and things we want to replicate. And I brought some of those for you today. So we looked at it should be kind of viney and webby. We could see that it's multi-layer, so it needs to have some kind of depth applied to it when you look at the storyboard pieces. There's also a bunch of centers that are connected for long bridges, and they kind of branch out and replicate from there. There are spores that are clustered in specific parts of that setup, closer to the center. Some of them will kind of escape that rule. There's really specific things about the corners of those intersections of that viney network. They all need to be rounded, so that's one of the key features that we were looking for when we were tasked to create that environment. And also, you guys can notice that every end of that network is kind of a hooky shape, right? So these were the features that we needed to tackle and develop for our setup. So how did it start, right? We already had an initial pass from layout. We were developing some models that we could, prototype the camera motion and see how it feels and see what could be interesting foreground, midground, and background. And production, brought in the effects in to help with that task, and they kind of gave me a lot of freedom to work on those, and I was super happy, and we were just kind of, okay, let's get creative with this. So when I think about, branches or viney things, I always think about L systems. And in Houdini, we have a really handy node that has a variety of presets that you can kind of sit and explore. So before designing any kind of algorithm, we just kind of went there and explored what's in the package. And I found this really interesting, the branching option. They look really interesting. I really liked how we kind of elongated and increased the iterations of it so you can get some really interesting shapes. And that's a really nice, interesting point for you to kind of get your variations and exploration started. So with that L system piece, I was just trying to see what can we get if we copy transform, rotate that around specific pivots, copy the same geometry back itself, or just mirror a little bit and apply some noises. And by doing that, we got some really interesting shapes. And when we kind of placed the camera around that mesh and navigated, we got some interesting, interesting overlaps and shapes. From there, we also experimented blurring the point positions, and to do that, we use the attribute blur, but we changed the type there from connectivity to proximity. That allows you to kind of blur the point positions. You get those really interesting organic shapes, and they are really similar to what we had in the storyboards. So from there, we think, okay, the skeleton is looking good. There is something that we can actually look at. So the next logical step is to kind of start working on the matching process. For that, we explored using p-scale and changed the scale based on how close we were from those initial clusters and how far along they were on the actual bridges. And we started playing with the VDB, polywire, but what really kind of made sense for us was to kind of convert it out to particles, do the VDB from particles there, and use the VDB smooth to kind of create those interesting arcs that you can see that on the screen. The main idea is that you can blur the position of the voxels, and by doing so, you get those really interesting arcs, and the VDB smooth node allows us to kind of tell how many voxels we actually want to blur or to average from. So that's kind of what we use, and that gave us that initial look that we were looking for. So I'm bringing in, that initial first look that we got. So that's the first time the team is looking at something that was done by FX with the actual materials, and we were really happy with we obviously had a lot to work on, but it was an interesting step to see, okay, we can get something that can be achieved here. So we iterate a little bit more, and we get some other shapes. This time we already not using the assets from the modeling department and relying only on the assets from the effects department. And we get, to play around with the camera, what's the foreground, what's the midground, and see how it goes. And I want to point out something about this current version, right? if you take a look on the tips, they are all really bland and they're really straight. And that's kind of not the reference, right? We are missing that hooky shape. So we came, and think, how can we approach that? So we were thinking, maybe we can just kind of create our own hooks and just copy them into the right places. But how do we find the right place in a really dense network that's kind of full of points, right? How do we go over that challenge? Our solution was to kind of use the neighbors lookup. The neighbor lookup actually allows us to go over and survey the mesh and find the tips and find the centers of each cluster. And by doing that, we're kind of able to say, okay, every time there is an end, we can just copy the hook, change a little bit and add some variation to it, and maybe play with the p-scale. So how does that happen inside of Houdini? It happens through a VEX function called neighbors count. Basically outputs for every point the number of neighbors that it has around it. So it can really easily from there create some kind of group. For example, the intersection group has 3 other brothers or 3 neighbors around it. As of the tips, they actually usually only gonna have 1 point nearby, so it's actually a tip. So by doing that, we're able to survey that really interesting mesh that we created with the L system and replicating that thing, and actually, being able to target those specific areas and copying whatever we want to that. So I'm now showing you guys, how it looked when we moved to that next step. Again, still really dense, really, you actually don't see those really boring hooks anymore. They all kind of have some kind of identity or feeling to it. And I also started playing with some of the, features on the actual mesh, just so we can see some, mounting noise applied to it, just to get some surface variation. So from there, we actually need to kind of start placing some of the spores. And to do that, we use an awesome node, that's the lab's thickness analysis. And that allows, again, to survey the mesh that we created. For this, we are using a proxy mesh. We don't need to rely on the high poly final mesh for that. We can just run that on the actual proxy mesh. And it's really versatile and handy node because you can actually ask to change where is the biggest part of the thickness is. So you can actually survey and create a mask in really specific corners. And by doing that, we were able, okay, if we had this really extensive network, now we have a way to identify all the clusters, right? And have a group, apply some fall off, apply some noises. And by doing that, we were able to now approach that one of the tasks that is scatter spores only around the big nucleus and not on the bridges. So we can, and to make sure that the scatters did not overlap with each other, we use a scatter line, so you can actually control the scale of the spore itself, but also its relationship to the nearby ones. So by doing that, you kind of have control so they kind of have a minimal overlap or even no overlap at all. The next part that we need to tackle for the shot is that this spore network needs to awake from a dormant step or dormant stage. And we started exploring different ways to do that, right? Because we had this really interesting relationship with the client where we're able to show and get feedback and do iterative work. So these are some of the variations we presented so we can get the conversation started. And how are we doing that? So basically, we have a mask that kind of navigates throughout that network. And by doing that, we can use that mask multiplied by something that's pushing it in specific areas. How does that happen behind the curtains? Basically, we're using the fire spread solver to do an infection of that network. And we did it over a really long range of the simulation. And then once we kind of get that mask and get that total burn attribute, we can just kind of wrangle it a little bit here. And one thing you guys can see here, we also added more splines in between, connecting different areas of the system, just so we kind of could propagate that data in a non-linear way. So once we have that kind of total burn attribute and we have a mask that kind of ranges throughout the simulation, it's really easy for us to remap that mask and actually select specific areas of that infection. And by doing so, we are able just to get a sort of a leading edge. So there's a lot of flexibility in that. So you can kind of change the p-scale or change anything you would like based on that mask. And that's kind of how it looks in Houdini. And how we are doing the deformation of the high-res mesh. So basically, we are using and doing all that infection in the lines and primitives basically allows us to do ultra-fast iterations. And it's the simming time is really, really short, but we just copy that over the high-res mesh. And add some velocities to the high-res mesh, and those velocities, we kind of using like a really high amplitude curl noise, and that allows us to kind of design or comb the velocities or comb the direction we want to push that mesh. So once we have the velocities and also the mask, we just multiply the current position by the velocity when the mask happens. So that's how we're actually pushing things around. And you can see how it looked in the end. We actually decided to not go forward with any propagation in the background. It's just a hint of that awakening. So for that, we just kind of did that in the first thing, that's the foreground element. All right, so in regards of the final image, yes, we split all of that in foreground, midground, segments. We also cache everything to ASS files. All of that's heavily, all that look you guys see here relies heavily on subsurface scattering. And again, procedural shading, looking at the curvature and using noises all around to get some nice variation. Next shot I want to talk about is the human cell attack. That shot's done by one of our artists called Darren. And it's a really interesting shot. It looks really complex when you first look at it, right? So we have things growing, we have to interact. This is a cell that's kind of wobbly, but let's see how he approached that. So first thing, we're just kind of splitting the tasks that we actually have in front of us. First one is to pierce the membrane. We will need to infect and grow from the center, and that growth needs to actually reach out the outer layers, and from there, we also need to play that out with the animation. So how did we go about it? For the membrane piercing, we are using material fracture just to fracture all the layers. And it's important for you all to understand that we actually do that step without the animation. So we freeze frame, bring to rest pose, do all the mesh processing that we need, and then we kind of move forward. So from there, we did the fractures. We bring back to the animation and did a simple, we did an interesting vellum cloth simulation to capture the piercing of the actual animation that we got into those membranes. Next, we want to talk about growth, and I just want to point out for you all that we're going to see some recurrent themes here. Although we didn't kind of share setups on this sequence, we all approach it in similar ways. So for the growth, we have an initial pop scene just to define the initial tendrils. And once we have those initial tendrils, we can actually stop that and start building branches from it. So in this approach, we create different layers in an iterative process that allows us to have a really interesting control of how that vining network needs to go on. So we define, how dense it needs to be, the actual noise patterns, and all these types of features in a rest pose, without the animation, and just kind of designing how we can actually make it look good. So from there, we also use the polywire to get an initial first pass of the base mesh, and how we can actually see the complexity, see the actual piece scale. And from there, we have all the mesh static, but we run a propagation algorithm, right? So similar to what we've been discussing here, we have a different propagation attribute here, algorithm here. It just looks at the nearby points and propagates a color, and that allows us to review those splines over time using masks. Let's take a look here on the solver. That infection happens in the subsolver. It based on the color propagation, and then we just add some age and do some PC open and PC filtering just to kind of mix with some noise, so it's just not really bland and really continuous. By doing so, we can get some nice variations. And after all of that is good, we just bring that into the space of the animation. We point deform, we do other techniques of deformation that allows us to kind of bring that really complex system into the actual animation. And those things play a part. Huge kudos to the WeFX Look Dev and lighting team for the amazing procedural shaders. I really love the way you can actually see a lot of the subsurface on that tendril that's kind of going inside when everything gets kind of grows, and you can see the shadows and hide all the things that are inside. I'm passionate about this sequence. The next part that we worked on was the parasite in a Petri dish. Shout out to our FX lead Vimal that took on this task. It also started with a storyboard interpretation. This is what we got. We had a cell that's gonna, shake it up, wake up, and it needs to rapidly explode and propagate and infect other humans. Basically, it's hunting human cells. That's what we're getting from it. And we tried different things We tested VDB advection, VDB growth, particles that follow lines, but none of that kind of really got what we needed, or it wasn't looked as dynamic as we wanted, right? Not really hunting any cells. So how did we go about it? So basically, we went around and developed a new growing solver with this. And it's really interesting about this process that it's super interactable, and it already kind of follows predefined masks. So you can actually create some masks and draw over your mesh so where you want it to go. And over time, it's actually going to use a series of attributes to find its best path, get to specific areas, and you grow some splines for you. After those splines are generated, we post-process them using p-scale variations. We look at point density and also age and a couple of the noise to actually allows us to build an intricate network. And this is another layer, so we have a couple different layers on that system that allows us to kind of have some depth variations on it. And for the final mesh, again, VDB2 set for the win, so we can actually remesh all of that and get some interesting flicker-free mesh. So a couple takeaways from this whole workflow and sequence that we worked on. Teamwork is a must. We had over 50 people working, in this amazing sequence, and it was a lot of work. Everybody contributed with ideas, solving problems. It was really a collective work, a collective push to kind of get this out. Proceduralism allows you to have more control and faster iterations. Imagine we had to actually wait for long flip sims or wait for simulations to run to actually get the feedback. We wouldn't kind of complete the job. So proceduralism allows us to kind of be really fast and have a lot of control what the choices we actually want to do for our systems. And I just want to point out that every time you look at a really complex VFX shot, be sure there is a lot of art-directable procedural solutions that are combined with simulations. It's a recipe for success when you kind of have short time and also need to do a lot of really custom work. So now we are open for questions. If anyone wants to kind of introduce, I'll bring back Mykyta back in. And yeah. Woo! All right, we have a question over there. Sorry.
So, hi. I love everything about that. That was awesome. There was clearly like a lot of love and art direction and just amazing talent that went behind that. I have a lot of like science questions because there was a lot of, I'm guessing, did you use any like references of like brain cell activity to build this and kind of further art direct the final result? And did you I have questions about like how you started to create the initial models for the cells. Were those actually human cells or are they modeled after animal cells?
Yeah, thank you so much for your compliments and on our work that we did. So the question was, how did we use the actual scientific references to build what we built? And it's a question with an answer yes and no both, because we had some initial references of cells that the client provided us with, the real cells and the real cell replication. But then we also needed to make sure that it looks alien and it looks like out of our world. Because we combined both the alien, the artistic creative look on top of the actual real look, we came up with this look that we have in the final shots. Thank you so much for the question.
Awesome. Thank you so much.
Thank you.
Any other questions?
Right.
Going once, going twice. Well, I think we answered it all. Great work, guys.
Thank you so
Excellent
much,
presentation.
guys.
Thank you.
Woo!